Considering the physics of the spring system again, what we have is a coiled spring and a mass, and the driving equation that will govern the motion of this mass is simply going to be Newton's second law, F equals ma. What we have here is the force, and the only force that's being applied horizontally is the spring force, and that is going to be k times x, so some spring constant times the displacement. But one quick little note, if we talk about the displacement x here being in the positive direction, then the spring force is going to act in the opposite direction. If I stretch the mass out to the positive side, the spring force is going to fight it and make it negative. However, if we also have x being negative, and so that would be putting the mass over on this side of 0, then what we're going to see is the spring force acting in the opposite direction, which will be a positive direction. So in both of those cases, whatever the sign of x is, the spring force is going to be the opposite sign or the negative of that. And so we can really capture the force of the spring best with this formulation here, negative kx. And since that's the only force that's being applied, we can quickly get to ma is equal to negative kx. Now that's not quite a differential equation yet. We don't see any derivatives, but of course, if we recall that the acceleration is going to be equal to the second derivative of our position with respect to time, then that's the same thing as replacing a with x double prime. So mx double prime is equal to negative kx. That is a wonderful differential equation. Very simple in form, but it has a relationship between x and its own second derivative. And that turns out to be a second order differential equation. Why? Well, because we have this second derivative of x inside the equation. So that's something new. We haven't worked with these at all before. Fortunately, there's some nice intuitions we can apply here. If we have, just to make life easy on ourselves, k and m both be 1, well, we had mx double prime equals kx, and if we use both values as 1, both of the constants as 1, just to see what we get, then it turns into x double prime is equal to, oops, forgot the negative sign. So negative kx is the spring force. What we get when mass is 1 kilogram and k is 1 Newton per meter is x double prime, the position, second derivative or acceleration, is going to equal negative x. Now we can actually do a little guess and check here. We're being asked to find, let's remind ourselves of that, the goal. Find x equals something. And what that's going to be is a prediction of the position over time. The solution is always a prediction. So if that's the case, well, we already know what the motion is going to be. It's going to be oscillations. What the math here is telling us is that we need to find x equal to something, which is equal to its own second derivative. So I take two derivatives, I get back to where I started, but with a negative out front. And if you think about functions like cos, x prime is going to be negative sine of t, and then x double prime is going to equal negative sine of t, negative cos of t. And if that's the case, hey, that is actually equal to negative what we started with, negative x. So in this particular scenario, our intuition, which is that the x that we would predict is some kind of oscillation, is validated by having the guess and check x equal cos t satisfying the differential equation. Of course, we could try something else as well. There's no reason why cos should be special. We could try sine of t, and if we pick x to be sine of t, then its first derivative is cos of t, then its second derivative is going to be the derivative of cos is negative sine of t, and lo and behold, if that was our x, sine of t, when we take its second derivative, we also get negative what we started with, negative x. So both of those are solutions. And what we can also do is find other ones if we want. We can actually say x equals, let's say, 7 sine of t. So put a multiplier out front. If we do that, the derivatives are just the same, except that we're going to have the 7 out front. And there we're going to have negative 7 sine of t. But once again, if we gather this part, we see that we get negative x. So cos of t satisfies the equation, sine of t does, 7 sine of t does, and now we have an open question. Are there any other solutions we should be looking for besides these? And what kind of, please, hopefully, is there a structure to the solutions that we can take advantage of so they don't have to keep looking forever? That's what we're going to do next. We're going to look at the general case of second-order linear differential equations and see how we can get some guarantees about when we can stop looking for solutions. The idea is we're going to unify these individual solutions and go from x equals cos of t, x equals sine of t as options, and to something that is the general solution. How can we combine those? And it turns out, again, fortunately, it's going to be a very straightforward process.